Hello dear students, we are going to discuss today on the concept of diffusion and dissolution part 2nd. Here we will discuss the factors affecting dissolution rate. Physicochemical properties of drug. Second, factors related to the dosage form. Third, effect of processing factors on dissolution. Fourth, factors relating dissolution apparatus. Fifth, factors relating dissolution test parameters. First, we will discuss about physicochemical properties of drugs. In that, first we will discuss drug solubility. According to the modified in Noyes-Witten equation, it could be easily understood that if the solubility of any drug will be more, the concentration of the stagnant layer will also be more, leading to a significant difference between concentration of drug in a stagnant layer and drug concentration in bulk layer, which will result into faster diffusion and ultimately faster rate of dissolution. Second, particle size. Diffusion layer theory equation, that is Noyes-Witten equation, clearly states the direct relationship of surface area with rate of dissolution, and it is well known fact that decreasing the particle size leads to increase in surface area. That means if we decreases the particle size, it will increase the dissolution rate. It is also a well known fact that micronization of sparingly soluble drugs leads to enormous increase in the surface area, conforming to the guarantee of better dissolution and bioavailability. Mere increase the surface area for better dissolution is not enough. The area exposed to the dissolution media is important for increased rate of dissolution. Next is salt formation. Salt formation of any poor soluble drug is one of the common approach being used to enhance the solubility of drug and dissolution rate. It has always been assumed that sodium salts dissolve faster than their corresponding insoluble acids, but it is not applicable to all the drugs, as in case of phenobarbital sodium salt shows slower dissolution. Another step is solid state characteristic. Various states of solid phase such as amorphous, crystalline, state of hydration etc. of any drug significantly affect to the dissolution rate. As example, amorphous form of novobiocin possess better solubility and dissolution in comparison to its crystalline form. It has also been reported that anhydrous form of any drug, that is thermodynamically more active than hydrates, get solubilized faster rather than its hydrated form. Example, ampicillin anhydrate has faster dissolution rate than its trihydrate form. Metastable, that is high activation energy, that is having high activation energy, polymorphic form have better dissolution than stable form. Next is factors related to the dosage form. Selection of excipients may significantly vary the dissolution of drug in formulation. At the similar time, poor formulation conditions and process may also affect to the dissolution and bioavailability. It has been generally observed that increasing the content of dried starch in tablet formulation shows gradual increase in the dissolution of the drug. Initially, it may be attributed to the fast disintegration due to starch, but later it was observed that the increase in solubility is just because of formation of hydrophobic layer of starch around the hydrophobic particle of drug. Microcrystalline cellulose is a very good disintegrating agent, but at high compression force it may retard drug dissolution. Similarly, the use of different binders and their concentration have also shown different effect on the dissolution behavior. Binders with high binding property retarded the dissolution process. Hydrophobic binders shows better dissolution than hydrophobic binders. Water soluble granulating agent Plasdone gives faster dissolution rate compared to gelatin. At the same time, it has also been observed that hydrophobic lubricants as metal stearate or magnesium stearate retards the dissolution of tablet, while the use of hydrophobic lubricants such as sodium lauryl sulfate increases the rate of dissolution. But the use of SLS is very limited. Hydrophobic lubricants such as metal stearates, talc, etc. decreases the effective drug solvent interfacial area by changing the surface characteristics of the tablet, resulting into poor wetting property. While the use of hydrophobic lubricants such as sodium lauryl sulfate creates a microenvironment of specific pH which leads to increment in the wetting of sparingly soluble weakly acidic drugs, but it has not a universal phenomena, as sodium stearate, water soluble lubricant, decreases the solubility of drug. At the similar time, it has been observed that the change in concentration of lubricants also affect to the pattern of dissolution. Whenever a surfactant material is added to the dissolution media, it also favors the dissolution of poorly soluble drugs, which may attribute it to the lowering of interfacial tension and increasing effective surface area. Example, sodium lauryl sulfate significantly increases dissolution rate of salicylic acid tablets. Third, effect of processing factor on dissolution. There are several processing factors such as method of granulation, size, density of granule, moisture content in granules and compression force used to formulate a tablet, which significantly affect to the dissolution rate. First, method of granulation. Generally, it has been observed that the granulation process increases the dissolution rate of poorly soluble drugs. Traditionally, wet granulation process is considered superior over the dry granulation or direct compression technique, but it has also been observed that during the granulation process, mixing of various excipient greatly affect to the dissolution rate. APOC, that is agglomerative phase of comminution, a newer technology, has also been founded to produce mechanically stronger tablet with higher dissolution rates rather than tablets prepared by wet granulation, which may be attributed to increased internal surface area of granules produced by APOC method. Second, compression force. The compression process influences density, porosity, hardness, disintegration time and dissolution of the tablet. Higher compression force increases the density and hardness of the tablet, while decreases porosity and hence penetrability of solvent into the tablet, retarding the wetting of formulation and decrease the dissolution rate of the tablet. Sometimes it has also been observed that higher compression force causes deformation, crushing or fracture of tablet particles into smaller one or convert spherical granules into disc-shaped particles with a large increase in the effective surface area leading to increase in dissolution rate. Next, drug excipient interaction. Drug excipient interaction during mixing, milling, blending, drying and granulating may lead to change in dissolution pattern and rate. For example, dissolution time of the prednisolone increases when the mixing time with magnesium stearate is increased. Similarly, if the mixing time of formulation containing maximum amount of microcrystalline cellulose or other slightly swelling disintegrating increases, it leads to enhanced dissolution rate. Autooxidation is a common phenomena when polysorbate 80 used as excipient in capsule leading to the formation of formaldehyde causing decreased dissolution rate of capsule. Next, storage condition. Core formation due to crystallization or aging is one of the common phenomena leading to decrease in dissolution. Absorption of moisture may be one of the more reason which results more binding capacity of the binder. Example, when acacia is used to form hydrochlorothiazide tablet as a granulating agent lead to decrease in dissolution rate during first year of aging at room temperature. Next, factor relating dissolution apparatus, that is agitation. Agitation of the dissolution fluid either leads to laminar flow of fluid or turbulent flow of fluid depending upon the intensity of agitation and type of technique used for agitation. When movement of fluid occurs because of agitation, it leads to the continuous changes at the liquid-solid interface between the drug and solvent. In simple word, we can say if the agitation speed gets increases, dissolution of any drug also increases depending on the shape and design of the agitator and physicochemical property of the drug. Apart from these things, there are some more factors related to agitator which may affect to the dissolution, such as position of agitator and sampling probe position. According to USP and National Formulary 15, axis of the steering element must not deviate more than 0.2 mm from the axis of the dissolution vessel. Sampling probe can affect the hydrodynamic of the system leading to the increased dissolution. USP and National Formulary states that sample should be removed at approximately half the distance from the basket or paddle to the dissolution medium and not closer than 1 centimeter to the side of the flask. Fifth one is factors relating dissolution test parameter. First one is temperature. Solubility of any drug is greatly affected by the temperature, which clearly indicates that any deviation in the temperature will significantly affect to the dissolution process. Generally, a temperature of 37 degree plus minus 0.5 is maintained during dissolution determination of oral dosage forms and suppositories. However, for topical preparations, temperature as low as 30 degree and 25 degree have been used. The diffusion coefficient D depends on the temperature. According to the Stokes equation, D equals to kT upon 6 pi eta r. K equals to Boltzmann constant. 6 pi eta r equals to Stokes force for spherical particles. Eta is equals to viscosity. R represents radius of the molecule. 6. Factors related to dissolution medium. There are several factors related to dissolution medium such as pH of the medium, viscosity, surface tension, which largely affect to the solubility of the drug. So, it is very important to select a proper dissolution medium for the dissolution study. First is effect of pH. Generally, a drug which is highly soluble or show pH independent solubility may achieve a sink condition at every pH. For such drugs, water may be taken as a dissolution medium, but in case of drugs with pH dependent solubility which maintains the sink condition at a specific pH range depending on the pKa of drug, dissolution medium should have the pH that provides sink condition. The pH of the medium should be chosen from the physiological pH range, considering the compatibility of dissolution medium with the drug. Generally, it has been observed that majority of acidic drug shows increased solubility with increasing pH. Dissolution media with pH of 1.2, 4.5 and 6.8 are starting point for medium selection if the drug has good solubility. USP buffers, example hydrochloric, acetate and phosphate buffers respectively are recommended for such studies. Second, surface tension of the dissolution medium. Wetting property and solubility of any poorly soluble drugs can be increased by lowering the contact angle. It simply means that by decreasing the surface tension, dissolution of drug may be enhanced significantly. Several literature shows that the increase in the concentration of surface active agents such as 2-in-80, sodium lauryl sulfate, etc. increases the dissolution of poorly water soluble drugs. Third, viscosity of the dissolution medium. Dissolution decreases with the increase in viscosity of the dissolution medium, especially in case of diffusion controlled dissolution process. According to the Bronner and Perot, dissolution of benzoic acid decreases with increase in viscosity of the medium, while in case of interfacial controlled dissolution process, viscosity does not play a significant role. The next is deaeration of dissolution medium. pH of the dissolution medium may vary due to dissolved air in distilled water affecting to the dissolution rate of drugs that are sensitive to pH change. At the similar time, air present in the system may form tiny bubbles on the surface of the tablet formulation, leading to the hydrophobicity and decreased wetting of the tablet, ultimately resulting the decreased dissolution. Now, we will move to the next module, in which we will discuss about the various official method used for dissolution. Module 5 contains various dissolution apparatus. Depending upon the dosage form, Indian Pharmacopoeia has introduced two apparatus, namely apparatus 1, that is paddle apparatus, and apparatus 2, that is basket apparatus. In paddle apparatus, we are using paddle, and in basket apparatus, we are using basket. Dissolution apparatus, according to British Pharmacopoeia, there are three apparatus designed by BP. Our first apparatus 1, that is basket apparatus, apparatus 2, that is paddle apparatus, and apparatus 3, that is flow through cell apparatus. Another dissolution apparatus, according to United States Pharmacopoeia, USP given 7 type of apparatus for the dissolution. First, apparatus 1, basket apparatus, and second apparatus 2, paddle apparatus. There are certain conditions which applied on both the method are mentioned below. First, the temperature of the medium is capped on 37 plus minus 5 degree centigrade. Second, the pH of the prescribed dissolution media should not vary by plus minus 0.05 unit according to specific monograph. Third, container capacity for retaining dissolution medium is 1000 ml. Fourth, distance between inside bottom of vessel and paddle basket is maintained at 25 plus minus 2 millimeter. Fifth, for enteric coated dosage form, it is first dissolved in 0.1 normal HCl and then in buffer of pH 6.8. Apparatus third, that is reciprocating cylinder. The assembly consists of a set of glass reciprocating cylinder, flat bottomed glass vessel having stainless steel fitting, type 316 or equivalent, and screen that are made of suitable non-sorbing and non-reactive material, that is polypropylene, and that are designed to fit the tops and bottoms of the reciprocating cylinders and the motor and drive assembly to reciprocate the cylinder vertically inside the vessel. The vessel are partially immersed in a suitable water bath of the convenient size that permit holding the temperature at 37 plus minus 0.5 degree during the test. The dosage unit is placed in reciprocating cylinder and the cylinder is allowed to move in upward and downward direction constantly. Release of drug into solvent within the cylinder measured. Basic modeling of the reciprocating cylinder could be better understood by the picture showing on your screen. Apparatus 4, flow through cell. The assembly have reservoir and pump for holding the dissolution medium, a flow through cell and a water bath that maintain the dissolution medium at 37 plus minus 5 degree. The cell size is specified in the individual monograph. The pump forces the dissolution medium upward through the flow-through cell. The schematic diagram of flow-through cell is just showing on your screen. Apparatus 5. Paddle over disc. Paddle over disc apparatus have paddle and vessel assembly similar to apparatus 2 with additional stainless steel disc assembly specially designed to hold the transdermal system at the bottom of the vessel. Apparatus 6. Cylinder. In this apparatus, stainless steel cylinder is used in place of basket in apparatus 1. The dosage unit is placed on the cylinder at the beginning of each test to the exterior of the cylinder such that the long axis of the system fits around the circumference of the cylinder and removes trapped air bubbles. Apparatus 7. Reciprocating holder. The assembly consists of a set of volumetrically calibrated solution container made of glass or other suitable inert material, a motor and drive-in assembly to reciprocate the system vertically, and a set of suitable sample holders. The solution containers are partially immersed in a suitable water bath of any convenient size that permit maintaining the temperature inside the container at 32 plus minus 0.5 degree C. Now we will talk about interpretation of dissolution rate. The given table interpret the condition of acceptance. Initially 6 tablets are taken, and if it not fulfills the criteria, other 6 tablets in step 2, and again if it completes the criteria, another 12 tablets are taken. We will interpret our dissolution results in 3 steps. First S1, second S2 and third S3. In first step, we will take 6 tablets. Each unit is not having less than amount of drug dissolved as per individual monograph plus minus 5%. In step 2, S2, again we will take 6 tablets. Average of 12 unit, that is 6 of S1 and 6 of S2 is equal to or greater than amount of drug dissolved as per individual monograph, and no unit is less than minus 15%. In step 3, that is S3, average of 24 units, that is S1 plus S2 and S3 is equal to or greater than amount of drug dissolved as per individual monograph are not more than 2 units, and no unit is less than 25%, where D equals to amount of drug dissolved as per individual monograph. Now we will come on the module 6, that is conclusion. Why we are studying dissolution? Dissolution is one of the important and critical parameter which has shown its importance in the development of various formulations. Increasing importance of the dissolution with enhancing effect of various guidelines has become an important tool for the industry, research, regulatory authorities and academia. Dissolution has become an important tool for detecting the effect of manufacturing variations and to control quality for ensuring batch to batch consistency. Dissolution of any formulation is being used as a predictive tool during the development of controlled drug delivery or sustained drug delivery system to show better in vitro in vivo correlation. With the development of newer formulation, dissolution study and related instruments have found new milestone but still need more development. This script focuses on the basics of dissolution with more emphasis over various equipments used for dissolution study. This content has been aimed to provide more accurate and precise knowledge to the student so that they could better perform in their coming future of research, industry or academia. Hope you all enjoyed this informative lecture. Thank you for your attention. Keep studying. Goodbye.